Welcome and thank you for joining this Tech Tuesday. My name is Billy, and today we're going to talk about the industrialization of additive manufacturing and how we at Combitech work with both polymers and metals and the path to value creation. I have been working with industrialization and technology development within the aerospace industry for 5 years at Saab before joining Combitech, where I have been a part of Saab's steering group for additive manufacturing. I have also been the topic manager for the EU project Combo 3D within Clean Sky 2. I'm currently working with internal Combitech project and as a manufacturing engineer for AM at an external customer. I have been interested in, some might say obsessed with additive manufacturing ever since I built my first 3D printer about 10 years ago. And I hope this presentation will serve as a small summary of how we work towards industrialization of additive manufacturing, as well as provide some insight in what we like to call the AM mindset. So I'm assuming most people already have some knowledge about Combitech, so I will only provide you with a short company introduction. Combitech is one of the Nordic region's leading consultant and solutions partners. We are based in Norway, Sweden, and Finland, and with more than 30 offices in strategic locations, we have a strong local presence. Combitech is fully owned by the Saab Group, but it is an independent subsidiary. We have a dual role. While we are a close partner to Saab, most of our work is done with external clients independently of Saab. A key motivation for us is to foster long-term relationships and to grow and develop alongside our customers. That's why our deliveries increasingly take the form of end-to-end solutions in which we are responsible for the client's projects, sub-projects, or an entire function. We operate in several different industries where we have specialized and deep industry knowledge, but we also think across industry boundaries since combined knowledge provides new opportunities. One of the areas we provide solutions for is additive manufacturing, where we have a very strong industry network. This industry network is one of our strengths when working with additive manufacturing. The core network we work with today involves all of Saab's business areas, Amexi and its co-owners, and external service providers. Combitech is a part of Saab and is represented in Saab's steering group for additive manufacturing, where we work together in common projects, research and development, and with Saab's AM strategies. Saab is also one of the co-owners of the company Amexi, which was founded as an initiative to gather all industries owned by the Wallenberg Foundation within the technical area of additive manufacturing, so that we have the resources available to advance the industrialization of additive manufacturing together. We also have a very good relationship with Siemens Energy, which is a global leader when it comes to serial production with additive manufacturing, where we have an established agreement on how we can cooperate with third-party business for serial production of additive manufacturing. This is the general process we follow when developing the AM capabilities of our customers, but of course it usually gets customized to fit with the customer needs and current knowledge and adoption of AM. The first step is always to build a general understanding of additive manufacturing, where you want to get an understanding of what AM processes and materials are available on the market and what the strengths and weaknesses are of the different processes. We would also be looking at how AM is applied within different industries today. After getting an understanding of the technologies that are available, the next step is to start looking at your own product portfolio and identify which applications of additive manufacturing could be the most relevant to your business. You identify values that can be achieved through additive manufacturing in your product portfolio and the services you provide. This enables you to form a strategy of which technologies to focus on moving forward, and to set up future goals and to start moving towards achieving them. After you have identified possible applications, you proceed to evaluate them. This can be done through a part screening and a part selection, where applications are evaluated in two different dimensions: the technical fit and the economical fit. Even though they are in many ways connected to each other, it's important not to confuse them with each other. While technical fit evaluates if a part can be printed with additive manufacturing, the economical fit evaluates if it makes sense to use AM for a certain part. From this, you start making business cases for applications and select which applications to move forward with. Identifying and evaluating applications should also be a recurring process, so you can adjust your strategy and your business cases as your understanding of AM increases and the maturity of AM technologies and materials on the market increase. We then proceed to further develop the business cases. You start to design your application for additive manufacturing, either through re-engineering an existing part for AM or from starting from a blank sheet. This starts with also defining the requirements of the part, depending on what the application is and the technology chosen, as well as making and evaluating functional prototypes. And this is then followed over by serial production. With our network, we at Combitech offer the ability to run R&D projects through all of these steps, from a basic understanding to serial production. And with Amexi as our R&D arm and testbed and service providers that take over when we move into serial production. I mentioned Amexi, which is located in Karlskoga, where they have built a state-of-the-art AM lab with production and material testing available in-house and partners for post-processing located nearby. This is our testbed for additive manufacturing. The owners of Amexi consists of these 12 companies that all work actively in additive manufacturing. And a huge advantage with this setup is that we don't have any competing operations within AM. This enables an open exchange between the companies. And this is a small preview of their lab. Additive manufacturing, which is sometimes referred to as 3D printing, is a collection of processes that share a common manufacturing method, which is making components through joining materials, usually layer by layer, in an additive process based on a 3D model. This makes AM different from traditional manufacturing processes, which rely on subtractive and formative processes. With additive manufacturing, we only add the material that we want in our component, compared to subtractive manufacturing, where we remove the unwanted material from a larger piece, and formative manufacturing processes, where we cast or form our material to the desired shape using tooling. And in the end, it's the production method, joining materials layer by layer from a 3D model, that allows us to create value with this manufacturing method. AM as a manufacturing method includes a wide variety of different technologies and terms. The most common way to classify and differentiate the technologies today is by grouping them into 7 main process categories, defined by a common ISO and ASTM standard. For printing polymers, we make use of powder bed processes, extrusion-based processes, and processes that relies on curing of light-activated polymers. For printing metals, we also make use of powder bed processes, but as well as welding processes and a wide variety of technologies that produce green bodies that can later be sintered into an end-use part. Some other materials you can print that are also good to be aware of are the extrusion of continuous fibers. This enables you to print fiber-reinforced polymer parts. You can also use binder jetting with sand or gypsum powder, which is often used to produce molds for castings. AM is already affecting entire industries by changing products, supply chains, and business models. But to achieve this, it's not enough to just take an existing product and put them in a 3D printer. What we need is a new way of thinking around value creation with additive manufacturing. And this is what we often refer to as the AM mindset. Understanding how additive manufacturing creates value for a specific application is key to success. And it is important to understand our goals with the technology. Instead of starting with analyzing if it's technically possible to produce something with additive manufacturing, it's often more beneficial to start with understanding which applications will produce the most value. We usually split value creation with additive manufacturing into three broad perspectives. How can we improve the product function and performance? How can we improve the supply chain for our products' life cycles? And how can we create a business model by capitalizing on these advantages? The large freedom of design that is possible with additive manufacturing and what we can do with the product is usually the first thing you hear about when talking about the value of additive manufacturing. You usually hear that complexity is free with AM, and this is generally true. The ability to create complex geometries without cost increases is one of the most powerful value creators for AM. It allows for organic shapes, lightweight structures, integrated cooling channels, and the ability to replace several components with a single AM part. We are traditionally used to producing designs with the constraints of our manufacturing processes. AM produces value by removing many of these old constraints. It is the first manufacturing process with these few constraints on geometry. As a designer, you need to understand the new design freedom and how it enables you to design for functionality instead of old process constraints. The pictured example here is from AIRBUS. They produced an art installation where steel wires were fastened onto nodes, as the one in the picture on the left. Each node was unique and welded by hand. On the right, you can see the result of a functional optimization of the same part, where the geometry has been topology optimized and all the components have been assembled and all components of the assembly has been consolidated into a single part. On the build plate of a printer, you can produce several different designs at the same time and keep iterating new nodes without affecting the production cost. This enables part customization. It is also important to understand how additive manufacturing can affect our supply chains. The values here will often surpass the value we are able to build into the product itself. Traditionally, supply chains are spread out by necessity. They involve many different steps that all require their own footprint, resulting in supply chains that involve several different companies and several locations. The complexity of these chains motivates larger production volumes and causes production to centralize. We are often hesitant to build up the same complexity at more locations than necessary. Additive manufacturing can create value by removing a lot of the spread and complexity of the supply chain. A component created through additive manufacturing will not require a foundry. It will require less machining and can avoid assembly steps. All of these steps can be contained within a single machine within its footprint. Not having to invest in tooling can make low volume production and individually customized components a very cost-effective option. We also have the freedom to move production closer to our end users. Since the only product-specific resource that needs to be distributed in this decentralized production is the digital 3D model of the component to be produced. The example in this picture is from the International Space Station. The tool pictured is the first bit of tooling manufactured in space from a 3D model sent from Earth, which is a good example how AM allows for decentralized production on site when needed. And to highlight an example where I've taken advantage of all these three areas for value creation, we will have a quick look at this pneumatic gripper for ball bearings created by Wittmann Robot Systems that has been completely redesigned for additive manufacturing. The old design consisted of a metal base plate with several pneumatic activators, all connected with hoses and connectors. The entire assembly is then mounted as an end effector on a robot arm that moves ball bearings in production line. Understanding different AM processes and their advantages and drawbacks is of course important, but the design process really starts with the end user and their challenges. Instead of taking existing components and adjusting them to make them printable, we have to rethink production from the ground up. Thereby, we can provide a design that is focused around function. So what is the key function of the product? What are the pain points with the current solution? How could the design flexibility of AM improve the design? And which AM process and material could be suitable for an application? Besides optimizing the design of the component, we also must analyze how we can improve the supply chain. AM is a digital manufacturing method which allows us to create supply chains that are less complex, with reduced lead time during both development and production. What challenges could exist in your current supply chain, and how could an updated design help solve these problems? What would be the best production setup? If we choose a production location close to our end users, we can provide shorter lead times, reduce shipping, and thereby get a lower environmental impact. And the last step is to understand if the current business model is still suitable, or if AM can affect parts of it. AM might not become the main driving force behind a company's business model, but it's still important to understand how AM can support your business model. This is challenging, but can lead to some major competitive advantages. So what is the pain points of the current business model, and how will the use of AM affect these problems? How could a new business model look like? In this case, instead of focusing on standard components or expensive and complex customized solutions, the company could now offer customized solutions with short lead times to possibly widen its customer base. AM is not going to be the end of traditional manufacturing methods, but it's a powerful new tool to add to your toolbox, bringing both new possibilities and challenges. AM offers the potential to produce parts in low quantities at a relatively low cost. This mainly comes from the fact that no tooling is required, which makes AM technologies generally very competitive for low to mid production volumes. AM also offers increased freedom of design when compared to traditional subtractive or formative manufacturing. However, AM processes are not without their own design guidelines and limitations. An AM part will usually need to be redesigned with AM in mind to be effective. Popular examples on how to do this includes part consolidation, topology optimization, internal channels, thin wall, and organic structures. One of the benefits which is lightweight design consists of methods and practices to make components and products weigh less while retaining or even enhancing their technical and mechanical functionality. This is one of the key applications for the design freedom that AM brings. This is usually achieved with design features such as lattice structures or topology optimization. Lightweighting can be very beneficial for low volume complex products that benefit from lower fuel consumptions. Another aspect of lightweighting a part is that minimizing the material in the part will usually lead to a shorter print time and thus lowering the manufacturing cost of the component. Functional optimization is another important topic that is enabled by additive manufacturing, and it involves using a design freedom to optimize our design. Often, our current designs are limited by what can be efficiently manufactured with traditional manufacturing methods. With the geometrical freedom enabled by many of the AM processes, we are able to remove bulk material, replace material with lattice structures, or even topology optimize our products and remove all the material that is not required for our loads. For a lot of applications, performance is key. For instance, an airplane that is light will consume less fuel and carry more cargo, and this increased performance will often motivate a higher component cost. Looking at supply chains of products can also provide opportunities to gain value from additive manufacturing by utilizing the flexibility of additive manufacturing. With additive manufacturing, we have the possibility to keep our raw materials on stock and manufacture our parts when they are needed, instead of keeping a costly supply of spare parts. The relatively small footprint of an additive production line enables us to set up production closer to our end users. We can also be sure that we're always supplying the latest version of our parts without it affecting our part cost. And this can be especially valuable for systems where downtime is expensive, such as oil rigs or airplanes, and the decentralized production where spare parts are required, such as the International Space Station, as well as industries that need to keep expensive spare part inventories, and where quick access to custom tools and fixtures are needed. Another big advantage with additive manufacturing is the ability to produce several different geometries on the same build plate in the same batch. One early adopter of this approach has been the hearing aid industry. Today, custom-fitted hearing aids are almost exclusively manufactured with additive manufacturing. Additive manufacturing is today used in a wide range of industries. Since its origin as a prototyping technology in the 80s, it has come a very long way. Today, applications can be found across the entire value chain, from prototyping to spare parts and repair. And I will end this presentation with a brief overview of different AM applications in different areas. The use of AM for prototyping during the product and development phase is probably the oldest and most widely used application. While often low-cost polymer technologies are used for prototyping, basically every technology available can be used. And depending on the development stage, prototyping can include simple visual models, but also functional prototypes to perform, for instance, flow testings. the possibility to quickly design, the possibility to quickly produce designs without needing to invest in tooling can save significant time and cost during the development of new parts. This is a case study by GE Aviation, showing how they are using AM to completely rethink their turboprop engine. The engine has been completely redesigned from the ground up, which additive manufacturing uses its main production technology. And this can produce parts that would be otherwise impossible to produce. This resulted in an engine that had a development time half that of what a traditional turboprop engine would have had. And some of the other benefits achieved was a 20% increased fuel efficiency, over 30% increased time between engine overhauls, and a more stable performance from the engine. By using AM in this application, they were able to consolidate over 800 individual parts into just 12 3D printed parts. The application areas for AM within tooling are also very diverse. Some examples include pressing and forming tools produced in metal, injection molding tools with optimized cooling channels for higher performance, and jigs and fixtures that are used during assembly processes. Besides just utilizing the design freedom that AM brings, advantages for tooling is usually being a lot more cost effective when produced in lower volumes, and have much shorter lead times compared to some traditional manufacturing methods. This case is from a company called POLYMER. And with the increase in robot manufacturing, with the increase of robots in manufacture and assembly lines, the production of grippers is on the rise. Production lines need to be as flexible as possible, and downtimes must be kept to a minimum. This makes additive manufacturing for entire grippers or certain gripping elements a perfect match. Their challenge was to design a gripping element in one piece that could be used for a wide range of applications. And their goal was to eliminate assembly operations to ensure quick changes of gripping fingers during maintenance. The pain points with their old design was the long lead times, complex manufacturing, and expensive downtime. The new design they were able to produce with additive manufacturing could be produced in an extrusion printer, meaning that design could be printed directly on site when needed with a very low production cost. Over the last years, additive manufacturing have developed from a tool that is mostly used for prototyping to a manufacturing technology for end-use applications in almost all industries. While many companies aim at using additive manufacturing to reduce manufacturing costs, the biggest potential can be realized when completely redesigning a product for its function. The design freedom can then significantly improve the performance of the part. This case is an hydraulic part for an AIRBUS A380. The objective in this case was to replace a conventionally manufactured valve block with an additive manufactured one. The part was produced by Liebherr Aerospace and was used in the AIRBUS A380. This is a primary flight control part that moves the spoiler of the aircraft to desired position during takeoff and landing, so it must meet some of the highest quality standards available. The original part was machined from a forged block with several machining and assembly operations, which led to a very limited design freedom and long lead times. So the main pain points were the weight of the part, since it was aerospace, and the qualification of and assembly into the very limited space of the aircraft. The design was optimized based on the installation space available, with the goal to keep as short connections as possible to the interfaces. And material was only added where it was necessary. This resulted in a part that weighed 35% less. And instead of simply building entirely new parts from scratch, AM can also be used to repair and build upon existing components. While there are some cases of companies realizing repair application with powder bed technologies, welding processes such as directed energy deposition enables easy application of material to existing parts. This offers a great potential to reduce costs and to shorten lead times, while at the same time, repairing parts reduces wastes and can help companies improve their carbon footprint. Directed energy deposition technologies, such as laser metal deposition, are already a mature technology in several industries. Expensive parts with high production costs can easily be repaired, meaning that the part or tool can be returned to use in a shorter time. Directed energy depositions allows users to reduce repair time, save costs, improve their carbon footprint by repairing worn out parts of a component instead of producing new parts. This is very effective for expensive parts, such as compressor blades in the aerospace industry, since they are costly to produce and usually come with a long lead time for spare parts and repairs. This can be especially costly when the product is unable to be used during its downtime. This picture from MAN shows how DED is used to repair the bearing surfaces of compressors and turbine engines. The parts they repair are often up to 8 meters long and can weigh up to 10 tons. The benefits here are high quality repairs and the reuse of expensive parts and materials, combined with a reduced downtime. Additive manufacturing also enables the production of spare parts in small quantities, which makes it a great fit for the technology. Some of the advantages of using AM are shorter lead times, reduced need to keep parts on stock, and there is no need for tooling. Also, the qualification process for spare parts are often less demanding than for a serial application. Pictured here is a JAS Gripen flying with a 3D printed plastic replacement hatch as part of a battlefield repair trial. And a case related to this comes from EVOBUS, who sees increasing challenges in the field of spare parts for their buses. The company's increasing product portfolio has resulted in over 300,000 different spare parts, which results in very high costs for warehousing and logistics, as well as long lead times. In addition, minimum purchasing volumes from the suppliers lead to overproduction and often to obsolete parts in their inventory. They have identified additive manufacturing with polymer parts as an application for interior parts of the bus. Several parts, such as covers and armrests from the interior of the bus, have been identified as suitable for additive manufacturing. The benefits here are that there are no minimum order quantities. There is a reduced need for warehousing of spare parts, as well as shorter lead times and a more sustainable solution to spares.